Hi, hello everyone, this is Matheus again, and on today's video I'm going to better exemplify how you can build a decision tree to base strategic decisions often valued in billions of dollars. Okay, so how you can reduce the risks of this decision making, having multiple project overviews prior to detailed work, how you can envision the cards on the table and see what options make sense for creating sustainable value for the project, and also to bring more sustainability in overall, or increase social, environmental, economic, technical performances altogether. So this is basically done by running multiple scenarios, testing as much hypotheses you have, and making this multivariate analysis. But here the intent of this video is to bring a more hands-on approach, how you can effectively make use of these possibilities. So in terms of the inputs necessary to use for MiningMath, here we need to have the block model already created with the geological information, etc., etc. And basically you can, whatever property you can model, which is based mainly on math expressions, this is something you can create inside your block model and further use as a constraint for your scenarios. So for example, based on the block's properties such as grades, lithology, hardness, etc., you can create functions, mathematical functions, and say, well, this block with this given set of properties will have this value for this property I'm just creating. It could be, for example, processing hours demanded in the mill. Okay, that could be an option. It could be based on the positioning of the block. I know that this block will demand a given amount of fuel consumption, etc., because of the average transportation distance, etc. And now I'm going to model the carbon dioxide equivalent emissions for this block. Okay, that's also a possibility. So this possibility, in fact, brings virtually unlimited opportunities for controlling different variables or properties you are able to model. Okay, so moving forward in terms of data formatting requirements. Okay, we have a few. Okay, let me just get back. Okay, so all we need is regular blocks. The block model should not be rotated. MiningMath doesn't allow for now the subblocks, so you need to regularize your block model or standardize it. We need ideally this rectangular base, not missing blocks over here, like some users sometimes often want to import an already optimized bit. So that's not ideal here because you're losing potential of the technology. You also need index coordinates, which are IJK coordinates basically. They should be sorted from the smallest value up to highest value. And I'll also notice that, for example, MineSite users, when creating index coordinates, the MineSite software starts counting the Z indexes downwards, and MiningMath will recognize these. In this case, the model is upside down. So ensure the IZ or K coordinate is starting upwards. Okay, this is mostly based on software conventions, so not a big issue at all. It's just to make sure the model is properly formatted in such cases. Okay. Also, MiningMath requires you to remove the error blocks prior to importation. So you need to use the topography wireframe in whatever mining package you are used to remove the blocks above the topography. Okay. The model should also be in the CSV format. MiningMath works with CSVs for inputs and outputs, which makes it able to connect to whatever mining package of your preference as well. Okay, in terms of required information inside the block model. So each block should have the following informations: the index coordinates. The block size is not necessarily a necessity to be inside the model, but it should be informed on the interface. Densities, grades, for how many grades you are working with. The economic math modeling, or the benefit function, at least for one function for the process and one function for the waste. Okay, slope angles as well. In this case, it's optional, and also control variables, which is what I was talking about, modeling different properties. And also, MiningMath allows to use stochastic models as well. Okay, here is a common format of a simple data set. As you can see here, I have the index coordinates being sorted from smallest to highest values. Grade information, copper, gold, slope angles, densities. Here I'm simply creating multiple economic values, columns for economic values. So notice that I know that this block is waste because it has no grade, but still I'm calculating the economic values for the processing stream as if this block could be ore. Okay, but as you can see over here, this value for the processing stream represents minus $300,000, while the waste, for the waste dump, this block has just $55,000. So based on the economic values, MiningMath will decide which is the ideal destination. Okay, here the discrepancy is great because we certainly know this is waste, but for intermediary blocks, or when having multiple processing streams, MiningMath's optimization will take care of the analysis of these trade-offs of mining or not a block, which destination to send each block, which would be ideal, when to mine, when to process, etc. Okay, here it's basically some tips and tricks, which is you can create as multiple columns as needed prior to importation. So here I'm creating several columns, like considering an increasing copper selling price in 5, 10, 20, 50%, and the same for decreases in the selling price. So afterwards, on the interface, after the importation, I will be able to select the proper column very easily and to use the proper information for each scenario. Okay, so this is a very useful tips and tricks. And also here I have the tonnage column. Of course, here it's just for a matter of example, because MiningMath will automatically calculate the tonnage of each block based on the block size, informed on the interface, and also based on the densities. Okay, the tonnage here is still something that could exemplify tonnage created for controlling different material types, for example. So you could say, well, this block has material type A, and here I will create a column called tonnage material A, and I will insert what is the tonnage of that material. Okay, and also I could create more columns for all the material types, all the rock types, or it could be to discriminate or describe inferred, indicated, and measured resources as well. It could be a way to further control the proportions of these sort of materials. Okay, so this is a possibility I would like to ensure you have in mind for this sort of modeling. Okay, here I'm creating also it's just an example of processing hours demanded or supposedly demanded for each block. Okay, so I could say, well, based on the properties of density, hardness, lithology, this block is likely to consume, considering the modelings, the formulations we are used to use, it will consume 14.87 hours in our comminution procedures, and then what I will just need to do on the interface is to set up the boundaries for these sort of constraint. Okay, so moving forward, let's go. The benefit function, as I was saying, you can add as multiple destinations as you might need, not a problem at all, and the optimization will take care of these trade-off analysis, considering the time value of money, the when, if, when, and to where sent each block. Okay, if mined or not, if processing or not, if when should be mined, when should be processed, etc. So here basically we have the economic function based on blocks revenue minus blocks costs, which is pretty much straightforward. Nothing new in this regard, I believe. So selling profit, processing costs, mining costs. Here you don't have processing costs, for example. And notice that you are creating these economic values for each destination for processing and waste, differently from all the software where you might assume a cutoff grade, and also based on that you will just create one economic value, and also predefining which destination each block should go to. Here there's no predefinition, and this decision will be solely based on the optimization and the internal trade-off analysis to maximize the net present value. Okay. Also notice that I'm not mentioning the here, of course, processing costs implies the recoveries are being applied here as well. But I'm not mentioning here the cutoff grades, because ideally you should not use the cutoff grades, because the cutoff it will be an optimized consequence of each set of constraints imposed to each scenario. Okay, so that's quite important to consider, because if you can use cutoff grades, but if you use them, you will likely to lose a few opportunities to maximize value. What you can do to, let's say, I need a minimum grade to feed my plant. Okay, that's pretty much reasonable. So in this case, you will need to control these grades, or you should control these grades, considering the average constraints which are used for blending purposes. And this will allow you to process marginal grade blocks, marginal grade ore, along with rich blocks. Okay, so that's the ideal way to work with these minimal market requirements in terms of quality of material being feeding the plant. Okay, so moving forward, over here we have more examples on economic values. As you can see here, I'm just exemplifying the possibility of having two processing streams, and for which we have different processing costs and recoveries. So these should be counted to differentiate the economic values of these different processing streams. Okay, just a simple example. Here we have an example on the Npv calculation made internally in the algorithm. So you might notice that processing plant considers the period mined is equal to period processed. So this is a block that is mined and processed at the same period. So the the net present value formulation is pretty much straightforward for processing and waste. Okay. And for the stocked blocks, there is a difference, because we have a period in which the block is mined and a period in which the block is processed. So here we have mining costs being applied within a given time frame, and here we have the processing costs being applied along with the revenue. So we have different time frames being considered over here for revenues and costs. So the calculation is this one over here. You will notice that you will need to insert on the interface the fixed mining cost we used before as part of the economic values, but this is just for MiningMath to do engineering reverse. reverse engineered, sorry, to better be able to identify the value used before and also to make the proper calculations. Okay, the rehandling cost, for example, is the cost for reclaiming a block that it has been stocked. So it's an additional cost. It's not part of the economic value formulation, but it will be part of on the interface as an additional cost that will be applied to only to the blocks that have been stocked and reclaimed. Okay, so just a few more examples on such possibilities. And here in the previous video I have explained a little bit of the interface, etc. So I'm going to skip these examples over here on the interface. Some animations or with a certain issue or too fast. Okay, I need to fix that. But the main idea here is how you can build your decision tree. So here I have a sample data set, the same which is going along with the MiningMath 1.1 installer. Okay, so I have the base case, about $900 million. Okay, we have the prediction charts, the mine sequence development, etc. And then we can change parameters. We can change the information for or the set of constraints, let's say, for assessing different possibilities, different chords on the table. So here, as I mentioned before, you just need to select the proper function to differentiate, for example, the different economic assumptions for the project. So here I'm assuming a copper increase in 10% in selling price. Okay, so what are the effects actually of this change? As you can see here, I increased the selling price in 10%. The NPV increased in 20% in comparison with the baseline. And also I have the prediction charts, the for example, the mine sequence, etc. And I can also change and consider what if the copper selling prices decreases in 10%. Okay, so we have these change over here. So as you can see, the predictions are changing accordingly. Here the baseline, the effects on NPV here were more linear. But this is not a guarantee. But you can see that in order to maximize value, the mining sequence is totally different, and of course here the assumptions were quite critical, and the reserves are changing drastically, probably. But the main point is that for each set of constraints, the mining sequence and indicators might change drastically. So the mine development could start from east to west and inverted completely, geometrically, let's say, the mining sequence. So we have a few cases reporting such drastic change, considering real data sets. So this is something to keep in mind about these possibilities. And what if we consider project ramp-ups or production ramp-ups or project expansions? Okay, here I'm getting back to the main economic function, the default economic function, but also considering the project expansion over here, considering different paragrains, different processing capacities, etc. So how these affects the baseline, how is these compared to the baseline? Here I have minus 15% in net present value. Here we have our prediction charts, etc. And what if I consider the same for the previous cases of increasing the selling price, etc.? So here I'm at the same value of the baseline. Okay, that's great. Let's change. Let's do the same for increasing the copper selling price. Here, as I have mentioned before, you can see that the change or the impacts on the net present value started to become non-linear. Because here we have the baseline, it has decreased to 15%. Here we have a decrease in 10%, and the net present value has decreased into 34%. And here it's keeping the baseline value, and also the waste ore profiles were changing slightly as well. Okay, constraints being respected. Here is how you can see the, for example, the mining sequence changing accordingly to each set of constraints being used. Here we have, for example, a consideration of an area to be protected up to period 4. So basically I'm using a restricted mining surface over here, which is defined as a grid of points. These points should be aligned with the block centroid. The surface file should be at the same size. Looking from a top view, it should be of the same size of the block model. Okay, and also I'm considering this. I'm considering to restrict mining up to period 4. How these will affect my project's value? In this case, it's considering an offset from a given region of 300 meters. How these affect the project's value? Is this important to government? Is this a mining right? Is this a cave to be preserved up to the end of the life of mine? Is this negotiable with the government? Is this negotiable with the society? How much value the mining company loses? How much job opportunities the society might lose? How much taxes the government might lose for public policies, for example. How each of these stakeholders are willing or open to negotiate or not. What are the impacts, and is this meaningful for the project or not? Okay, so this is the sort of evaluation you can do with the MiningMath by assessing these different possibilities. So here, considering the 300 meters protection, we can see that the baseline value has been preserved. And what if we consider an offset of 400 meters? Okay, for 400 meters, this value for the project is still keeping the same for this case, for this set of constraints. But for a different project, it could represent 3%. It's much or not? Is it much or not? How impacting or such change? So maybe we could be doing a huge efforts to negotiate these areas, but they won't affect the value of the project. Maybe they will, and we're not doing so much as we should. So this will also be an opportunity for managers to guide their teams to work on the biggest issues for the project and also to move forward faster. Okay, so how do these project assumptions affect the mining sequence? Here I'm always filtering the same period 4, just to see an intermediary period or the middle, let's say, of the life of mine. But here we can see that the mining sequence is changing accordingly to preserve value. The project assumption has changed. This scenario is more constrained than this one, but the mining sequence has changed slightly to preserve as much value as the baseline and as much value as this case as well. So these are the sort of opportunities you can assess. So here comparing with the baseline, for example, I'm considering reduced minimum mining widths and an increased vertical rate of advancement. What does that mean? This means I'm increasing selectivity. Okay, and how could these help the project? Okay, but here we have the baseline, or the comparison of this case with the baseline is minus 15%. Okay, that's pretty much interesting. In terms of predictions, here I have the base case, here I have the predictions for this case over here, and also we can see that the waste profile changes slightly as well. So how does this affect the mining sequence? As you can see here, in this case they are a bit similar. Here it's mining more of the northeast, here it's mining more of the west side of the pit, etc. So there are subtle changes in the mine operational aspects of the mining development to comply and to maximize value, to preserve as much value as possible for any set of constraints. That's the main part main point over here. And what if we need to increase or to better constrain the average of copper? Here we're just defining limits, minimal and maximum limits of 0.5, 0.7, and how does these affect the project? Here we have a minus 14% in comparison with the baseline. We have the prediction charts, the optimum cutoff for copper, oscillating over time as well. The stockpile is unlimited in this case. So as you can see, it's taking to maximize value. It's taking at most 15 million tons. Okay, and what if we reduce? We cannot have such a stockpile. We should work with the limit of 5 million tons. Okay, let's change. How does this affect the project? Here we can see that the grades are being controlled. We have the maximum, the optimal cutoff also has changed slightly for the last period, especially. Also the production profiles also changing, and here we can see that the stockpile is now limited to 5 million tons. And for this reason, we have lost 2 percentile points in comparison with the previous case, minus 16% compared with the baseline. And so this value or this change represents 18 million tons. Okay, $18 million. So is it possible? Is this sufficient to have a bigger stockpile, to liberate a certain area, etc., or not? How these could we cope with this challenge, or how could we cope with this information and maybe adjust our strategy to comply with or to preserve as much value as possible? Okay, so a few possibilities in this regard as well. Here, as I was mentioning, the average processing hours, 13,000 hours for, let's say, for the mill. And how does these affect the project? Here we can see the prediction profiles, the processing hours being respected, and the profiles, the profile of hours demanded over time as well. And well, maybe sometimes I have more flexibility in terms of how much tonnage could I process. Okay, but maybe the bottleneck is within the processing hours, so that's a possibility as well. So how does this affect the project? Here I'm relaxing, or let's say I'm increasing the prediction capacity of my plant in 10%, so 33 billion tons per period, and also keeping the same processing hours. What are the changes in this regard? Here I'm managing to recover value because I increased the prediction capacity, and the processing hours are still the same. They are still close to the limit for years from year 1 up to period 10. Actually, I'm saying year, but it could be a month, a semester, etc. And also for period 11, it's dramatically lower than before. Okay, also the prediction profiles were changing, but I managed to recover a little bit of my value, so I'm just 3% lower than the baseline in comparison with the previous case. It was 7%. Okay, so these were the changes. So I know that in this case my bottleneck is not in the processing hours available, it's in the prediction capacities, but it could be different for each case. So these were a few of the possibilities to build your decision tree and to better understand the possibilities or the paths to create sustainable value, to deliver more value to society. And any mining company that is willing to be a leading company in terms of sustainability should be committed to making the most efforts it could to ensure this decision making is as robust as it could be, and having plenty of paths being analyzed simultaneously. So if you want to commit to this future, to bring more sustainability to your business, please let me know and contact me at support@miningmath.com. Thank you very much, and see you on the next time. Thank you.